Welcome to Lesson 6 of Puzzles to Exercise the Mind. The Prisoner's Dilemma. For some reason, a lot of puzzles involve prisoners. Not my idea, I didn't create these, but we have yet another puzzle concerning prisoners. This is a classic one from game theory. So we'll introduce game theory also as part of the solution here. So two people are arrested and imprisoned for grand theft. The prisoners are not able to communicate with each other. This is during the process of negotiation in terms of a plea deal, which we're going to talk about here. So the prosecutor does not have enough evidence to convict the pair on the principal charge, in other words, the grand theft. So the plan is to sentence both to a year in prison on a lesser charge. However, the prosecutor decides to offer each prisoner a plea bargain. If he testifies against his partner, he will go free while the partner will get 10 years in prison on the main charge. However, if each prisoner testifies against each other, both will be sentenced to 2 years in jail. The prisoners are given a little time to think this over, but in no case may either learn what the other has decided until he has irrevocably made his decision. Each is informed that the other prisoner is being offered the very same deal. What should each prisoner do to minimize their time in jail? Okay, so they're not able to talk to each other, just to make it clear. The puzzle, it kind of depends on the prisoners thinking logically what's the best solution for each of them, given what the other prisoner may decide. So that's how we'll solve the problem, but I'll give you a moment to think about it. So just to summarize what I said on the previous slide, before I give you the answer on the next slide, we have a table here. So it shows what can happen in either case here. The way to read this is if prisoner A remains silent and declines the plea deal, and B remains silent, then they each serve 1 year. If A remains silent and B testifies, then A goes to jail for 10 years and B goes free. And then the other way around, if A testifies and B remains silent, A goes free and B goes to jail for 10 years. And then if they both take the plea deal, they each serve 2 years. Okay, so that's just a summary of what I showed you on the last slide. And just to emphasize the conditions, the prisoners are separated into individual rooms that cannot communicate with each other. So they know what each that the other prisoner has been offered in terms of the deal, but they know this table basically. They each know this table. Although maybe it's not presented to them this way, but they know the information in this table. And they can't talk to each other and negotiate. And they understand logically how to work through this. And they don't trust each other. They have no loyalty to each other. And also there's no after effects. So there's no opportunity for retribution or reward outside of the game. So once they're outside of the trial, I should say here. Okay, so those are the conditions, and I'll give you the answer, or at least I'll work through it in the next slide and describe if they think logically what they're going to do, and the paradox. You may see the paradox already, but I'll describe that on the next slide. Okay, so I have the table here again, and what we're going to do is analyze it from the perspective of prisoner A, and then I'll claim that B has the same conclusion, thinking logically, and that's clear because this table is exactly symmetric. So this is A's reasoning before he makes a decision, or in the process of making a decision, and he looks at each possible response from B. So A says, all right, let's say B remains silent and cooperates. What's the best thing for me to do? If I also remain silent, Um, I get 1 year in prison along with my partner. But what if I testify? I go free, and my partner gets 10 years in jail, and I don't care about him at all. So I'm gonna testify in this case if B remains silent. So that would be A's conclusion as terms of his best decision. Then A looks at the possibilities if B testifies, and A says, well, if B testifies and I remain silent, I'm going to go to prison for 10 years. So I don't like that. What if I testify? What if I also testify? And again, that A would have only 2 years as opposed to 10 years. So A's saying, all right, then I'll testify in this case too. So A's reasoning is whether B remains silent or whether B defects, A's best approach is to defect, because in one case A goes free, in the other case A gets 2 years versus 10. So A decides, well, it seems like the best thing for me is to testify since I don't trust B. And then B looks at this and does the same analysis and says, yeah, I'm gonna testify against my partner. So they both end up with 2 years in prison, and they miss out. That's the paradox here. They miss out on the better solution. So even if they were allowed to talk to each other, they don't trust each other, and they might still do this here. So, excuse me. So that's the paradox of this problem, and in general, it's a type of paradox that game theory exposes. And you may argue this is not the most practical or probable type of situation, but it is used, game theory is used, and you can envision maybe a military application where there's more options for both sides. They don't trust each other, they don't talk to each other. Just to throw out an example off the top of my head, like maybe creating more nuclear weapons. Neither side trust each other, so they take the option 2 here. They don't want to get blown up by the other side, so they both build more and more nuclear weapons. But if they actually trusted each other and cooperated, then they would have this simpler solution here. So that's the nature of game theory, and it's quite interesting. There's entire books on the topic, and I'll give you a few references on a couple of slides after. One of the pioneers in game theory was a famous mathematician from the last century, John von Neumann. He was from Hungary. You see his years birth and death here, 1903 to 1957. He has an amazing prodigy as a child. He could speak 8 languages by the age of 6, including ancient Greek and Latin. He could divide 8-digit numbers in his head at the age of 6. He was familiar with differential and integral calculus by the age of 8. He entered the University of Budapest at the age of 15 and earned a degree in chemical engineering at 19, and got his PhD at the University of Berlin at age 22. He left Hungary for the United States because of the rise of the Nazis. He was Jewish. He became part of the Manhattan Project that built the nuclear weapon during the Second World War, and apparently he was exposed, I guess, during some of the testing, and in fact he died from that exposure. That's why such a young age here that he passed away. So amazing intellect. His book on game theory was another gentleman. I forget his name, but it was quite a long book that sets a lot of the theory in place. He's also known for doing a lot of the theory behind computer science. So, quite an interesting individual. If you get a chance, go to the Wikipedia page, and there's even more background on him there. I have a couple of references for you here. There's a free book from a professor at the University of California, Davis. I'll put these links in the in the description to the video, so you can just click on them. You don't need to copy them down here. And this seemed to be a fundamental book, not too hard to read. And then I also I have a book, Mathematical Vignettes, where I have relatively short summaries, like 20 to 40 page summaries of different topics, and I have a section on game theory. And you might want to pick that up. It's free. The electronic version is free, and again, I'll put a link to my web page there when you can download this book. I have what I call the traffic light puzzle. It really doesn't have anything to do with traffic lights. It's just that I use the colors here that kind of look like a traffic light. What we have here are three numbers. One here, the second one, the third one, and we're adding them together. We're getting a fourth number. And each of the circles represents a different, actually it could be the same, a single digit. So from 0 to 9, so green could be 0 to 9, yellow could be 0 to 9, and red could be 0 to 9. And whatever it turns out for red has to be all three of these are the same number. All three of these are the same number, and all the green are the same number. So what is the sum, and then what are the values of each of the colors? So I'll pause here for a few seconds, and then I'll come back on the same slide and give you an answer. It's not too hard. Just try working from the right and testing different numbers to see what works out. Okay, I'm back. Let's try from, as I say, try from the right. Let's see if 0 works. Yep. If you put in 0 here, you get 0. And then these would all be 0. And then that working backwards, that would mean both red and yellow would be 0. So one solution is 0 for everything. That's not the one I was looking for. It's not very interesting. But just to be complete, I'll mention that 0 is a solution. All right, so the next step is to go through 1 to 9 and see when you add them up if you get the same number here. Now, of course, you're going to have a carryover, and so that's something to keep in mind. So you add 1 plus 1 plus 1, you get 3, and 3 is different from 1, so that's not going to work. 2 plus 2 plus 2 is 6. So 2 and 6 are not the same, so that's not going to work either. Okay, I won't torture you with going through each one of those, but I'll give you the answer for green. It's 5, and that's the only digit other than 0. When you add 5 3 times, you're going to get 15, but that's fine because you can just carry over the 1. So you get 5 plus 5 plus 5 is 15. You carry the 1, and we get 5 5 5 is the sum. And now these three numbers are the same, right? They have the same 3 digits. So we can just divide 555 by 3, and that's 185. You can check that out. It's 185. And let's just see if that works. That implies that red is 1 and yellow is 8. So let's see if that works, if 185 works in here. So we have 5 plus 5 is 15. We carry the 1. 3 8 is 24. And we add 1 to it, so it's 25. So yeah, we got a 5 again here. And then 2 added to 1 is 5. So it does work out. On the next few slides, I'm going to talk about something known as Pascal's triangle. I'll give you a little bit of the history on the next slide. So here we have an example of just a few of the rows. It goes off infinitely long. You see we have 1s down along the left and 1s along the right. And then we have 1, 2, 3, 4, 5, 6, 7, and so on in the next diagonal, and the same thing on the other side. There's a little bit of complexity here in how these are computed, and I'll explain that in a minute. But as an exercise, why don't you pause the video, and I'll come back in a few seconds, and then I'll explain how these numbers are generated. Okay, I'm back. Hopefully you figured it out. If not, let me explain. So I can draw it in here. So the 3 is from the 1 and the 2 being added together. Same thing here. And it's the same pattern everywhere. Let's take another one. The 10 is the 4 and the 6 directly above it. This 15 down here is the 10 and the 5 added together. So we can do the next row. We'd put a 1 here, and then it would be 7, right? 1 and 6 would give you a 7. Then 6 and 15 is 21. 35, 35 again, and 21, 7, and then 1. There's a rather long history concerning Pascal's triangle. It wasn't always called that. In fact, it's only given that name in the West. There's other names for it I'll mention here. This what I have here is a summary of information I got from Wikipedia. I have the reference down here. If you just do a search on Pascal's triangle Wikipedia, you'll get this. Go to this link. So the pattern in the West is named after Blaise Pascal. He was a mathematician, a physicist. He lived from 1623 to 1662, and as I mentioned, the structure was known long before Pascal's time. He died only at the age of 39. According to the Wikipedia article, they never completely found the cause of his death, but there was speculation it might have been tuberculosis or stomach cancer or some combination of the two, but there was never a definitive diagnosis there. The Persian mathematician Al-Karaji wrote a now lost book which contained the first description of Pascal's triangle. At least this is according to Wikipedia. They're going back even much further. The Indian lyricist Pingala, 3rd or 2nd century BC, somewhat cryptically described the method for counting meters. This is related to poetry, I assume, that is equivalent to Pascal's triangle. So I guess you're somehow creating poetry based on that summation technique that I mentioned in the previous slide. And then the Persian mathematician Omar Khayyam apparently also used the same pattern. I don't think he was aware, the Wikipedia article didn't clarify, but I don't think he was aware of what Pingala had done. So I guess the idea was he independently and somewhere between 1048 and 1131, he came up with a similar pattern. And then it's Pascal's triangle was known in China during the 11th century. It's AD through the work of Chinese mathematician Jia Zhang. And apologies if I pronounced that wrong. He lived from 1010 to 1070. and during the 13th century, Yang Hui defined the triangle, and it is known as Yang Hui's triangle in China. So again, I got all this from Wikipedia, which makes it a little bit interesting is they're claiming that the first description was from Al-Karaji, and this description here, I guess it is a little bit later, but this description here, I'm going to show you what it looks like on the next page, and it's clearly Pascal's triangle. It's just different notation, but it's very clearly the same thing. I'll show you that on the next slide. Again, I got that picture from Wikipedia article. I got this from Wikipedia. It's public domain as far as I understand. It's from Wang Hui's triangle, what I mentioned on the previous slide. And you can see it's clearly the same thing as Pascal's triangle. This is a 1. You have 2 1s here. You have 1s down the sides. 1 plus 1 is 2, these 2 slashes. You have 1, 3 slashes is 3, 4, 5, 6 is this symbol here, 7, 8. You can check a few of the ones in the middle here. 3 plus 3 is 6. That checks out. Then 4 and 6 is 10. I guess this symbol is for 10. 10 and 10 is 20. I guess 2 slashes and a little 0 is 20. So very methodical. It all makes sense. All this, of course, on the side is in Chinese. But clearly this was discovered before the work of Pascal in the 17th century. So yeah, quite interesting, and it's kind of easy to figure out what these numbers are just by guessing and working what's in Pascal's triangle. We have a few more patterns on this slide. Let's look on the right here first. The rows add up to powers of 2. If you see here, the first one is 2 to the 0, which is 1. Then this is 2, so 2 to the 1 power. Then this is 4, it's 2 squared. You add these numbers up, you get 8, that's 2 cubed. We can go all the way down to this row here, and you get 15 and 15 and 30 plus 20 is 50. Then 7, 7 is 64. That's 2 to the 6th. If you went to the next row and added up the numbers, you would get 2 to the 7th. So that's one pattern. A similar pattern is if you do plus and minuses. So you have 1 minus 4 plus 6 minus 4 plus 1, and you have the two minuses here, so that's minus 8. And then the 1, the 6, and the 1 is plus 8, and you get 0. So if you take alternating sums here, 1 minus 5 plus 10 minus 10 plus 5 minus 1, excuse me, you add up to 0. So alternating plus and minus on these rows adds to 0. Yet another pattern is if you take x plus y to a power. For example, the second power, you get x squared plus 2xy plus y squared. You notice the coefficients are 1, 2, and 1, which we have here. If you do it for x to the 4th, excuse me, x plus y to the 4th, you get x fourth, then 4 times x cubed y, then 6 times x squared y squared, 4 times xy cubed, and then finally just y to the 4th. You can do it for x plus y to the 5th. You just need to remember the pattern here. The values, the powers of x go down and the powers of y go up. So you would just start with, if you did this row here, you would have x to the 5th and then 5, x to the 4th, y, and so on. Pascal's triangle is related to combinations. Remember when we talked about probabilities a few lessons ago, we had to count the number of cards and other similar problems where we had the number of ways of choosing. For example, I have here highlighted in red 5, choose 3. So we had 5 distinct objects, and how many ways could we make a set of size 3 from that? And here was the combination. The formula was 5 factorial over 5 minus 3 factorial times 3 factorial, and then you get this. And the 3 factorial cancels the first 3 terms in this, and you get 4 times 5 divided by 2, and that's 10. You notice this is that number there. And 5 choose 2 is also 10. And you have the same thing all the way across this row here. If you evaluate each one of these, you'll get these numbers here. If you go down another row, and you just have 6 choose 0, 6 choose 1, 6 choose 2, and so on, you'll get these numbers here. So it's perhaps a shortcut for computing these factorials. You can just go between this triangle here and Pascal's triangle. They're basically the same thing. It's just that when you evaluate these, you get the numbers. So yet another interesting pattern that we have. Here's another pattern. It's sometimes called the hockey stick pattern because it's sort of a hockey stick shape. But you can take any of these shapes. I showed one here in red. If you take 1 plus 2 plus 3 plus 4, you get 10. You can go down another way here. 1 plus 3 plus 6 plus 10. That's 16, and 4, it's 20. You get 20. If you extended this a few more rows, you could find more patterns. Here's another one, 1, 2, 3, 4, 5. That'll give you 15. So this here. And there's an infinite number of these hockey sticks embedded in here that sum up the way I just mentioned. We have more patterns here. We have the natural numbers if you go diagonally down this way. 1, 2, 3, 4, 5, 6, 7, so on. We have the triangular numbers. 1, 3, 6, 10, 15, and that's just stacking balls one above the other. So 1, and you see 3, and this is 6. The next one would look like the bowling pins. It would be 10, and you just continue down. The next one's 15. One you may not have seen before is tetrahedral numbers. First one is 1. It's just one cannonball, say, and then you have 1 stacked on top of 3. That gives you 4. And you can't see them all down here, but this would be 6. So you have 1 plus 3 plus 6, that's 10. Then if you did the same, if you made another layer of bowling balls, you would have 20. And so these are called tetrahedral numbers. The next ones are not possible to visualize. They're 4-dimensional. It's sort of like this figure in 4 dimensions. I won't try to explain it, but they're called pentalope numbers, and they're 1, 5, 15. The next one would be what? 20 and 15, so it would be 35. And there's probably something in the 5th dimension, but I'm not going to talk about that either, but that would go along this diagonal here. I want to switch gears a little bit here and talk about the Fibonacci sequence. As we'll see later, this is related to the Pascal's triangle, but let's introduce it first. This is part of the sequence. 1, 1, 2, 3, 5, 8, 13, 21. Can you see what the next number is? If not, pause the video and I'll come back in a few seconds and then I'll explain how this is generated. Okay, I'm back. Here's how it works. The first 2 numbers are given, and then you add these to get the next one. You get 2. Then 1 and 2 is 3. 2 and 3 is 5, and so on. So the next number here would be 13 and 21. So 34. And then the number after that would be 21 and 34. It's 55, and so on. This sequence and thousands of other sequences are listed in this online site, Online Encyclopedia of Integer Sequences, the OEIS, and you can go to this location here, ois.org, and you get a whole bunch of information on this sequence. I'll give you a little bit, but this has a huge amount of references. There's many sequences listed there, as I noted, and you can actually, if you found a sequence for some reason and you didn't know what the next number was, you have a good chance of, if it's a known sequence, of just typing that in the search button and at this site, and it'll actually come back and tell you what sequence. So you could try this here. Try going up to 8 or 13 and plugging that into the search on this site, and it'll tell you it's the Fibonacci sequence. So here's the formal or technical definition. So the nth number, f sub n, whatever that happens to be, so this one's here, say 8, is just the sum of the 2 previous numbers. That's what this is saying here. And amazingly, there's a formula for directly computing the nth Fibonacci number without going through the recursion. And even more amazing is what the formula looks like. I'll show you that in a second. It's called Benet's formula, and here it is. Isn't that amazing? So if you wanted the 10th Fibonacci number in this sequence here, you would take this number, raise it to the 10th power, divide by the square root of 5, and then you would subtract almost the same thing. You notice it's 1 minus. This is a plus here. We'd raise this to the 10th power and then divide by the square root of 5 again and subtract it. And you would get exactly the 10th Fibonacci number. Yeah, the other thing I want to note here is I'm not going to go too deeply into or at all really, the golden ratio, but that's this number here, 1 plus the square root of 5 divided by 2. That comes up a lot in mathematics. There's actually an entire book on the golden, probably more than one book, but I'm aware of at least one book on the golden ratio. I'll put the link to that book in the description of this video in case you're interested in that. But it's a proportion that comes up quite often in art and in architecture, and it's related to the Fibonacci sequence in this way. So we have another example here where something is named after a person, and in fact it was discovered much earlier. So the Fibonacci numbers were first described in Indian mathematics as early as 200 BC by Pascal. Remember I mentioned him earlier, on enumerating possible patterns of the Sanskrit poetry formed from symbols of two lengths. Currently, the Fibonacci numbers are named after the Italian mathematician Leonardo of Pisa. I think Fibonacci might have been a nickname for him, who introduced the sequence to Western Europe mathematics in his 2002 book Liber Abaci. There's actually a journal, the Fibonacci Quarterly, that's devoted to this number and things related. There's a lot of things related to its number, so I guess that gives enough ammunition for people to write articles. And you can go to the website here, which I've listed. I have a bit of an exercise here. We have a pattern. 1, 1, 2, 3, 4, 6, 9, 13, 19, 28, 41. The first three numbers are sort of the input, just the way we had 1, 1 as being the input into the Fibonacci sequence, and then the other numbers are based on some pattern. So again, I'll pause here, and you may want to see if you can figure it out. It's a recursive pattern, but it's a little bit different from the one used in the Fibonacci sequence. Okay, I'm back. Let's see if you got it. I'll explain it here. So the first one in the pattern is the 3, and it's the number before it and then 3 numbers back. You go to 4, and it's the number before it and then 3 numbers back. So 1 and 3 numbers beforehand. Let's try a little bit further up here. So 28 is 19, and then the third number here, so 9 and 19, that would give you the 28. 41 is 28 and 13. So if you wanted the next one, it would be 41 and 19. So that would be 60. In general, these are known as recurrence patterns. So if we wanted to write this down, I don't know what we would call this. Let's just call it a G. G sub n would equal G sub n minus 1 plus G sub n minus 3. That would be the recurrence formula for this particular pattern. There's something called the Fibonacci squares. You can see here we started with the first two numbers, 1, 1. We put them next to each other. Then we put the 2 on top, since the two ones together would give you a base of length 2. Then you get a base of length 3, so you put the next Fibonacci number here. You get 3 plus 1 plus 1, you get or 3 plus 2 if you like, and you get the next one, and then 3 plus 5 is this length, and that's 8. And you can see the pattern 13, 21. So this is known as the Fibonacci square. No puzzle here, just thought it was a nice, pretty picture to put down. And I got it from the Wikipedia Commons. Here's the link to this figure, and we have a similar figure related to this. I'll show you on the next slide. So here we have the Fibonacci squares, but you notice we're going from corner to corner diagonally. So we have from 1, then 1, then we go from this corner to this corner using an arc, a quarter circle, I guess. Then you go from here to here, here to here, and you get this really pretty spiral going out indefinitely, and that's known as the Fibonacci spiral. And again, I got this from Wikipedia Commons. Here's the link to that. If we take the Pascal's triangle and we line up everything to the left, as I've shown here, so you notice we still have all the ones going this way and this way. I've just shifted them over this in this form here. And then if you draw diagonals and you add the numbers along the diagonals, you get 1, 1, 1 plus 1 is 2, 2 plus 1 is 3, 5. You get the Fibonacci numbers. So yet another pattern embedded in the Pascal triangle, and I got this figure just to give credit to the source from Wikipedia Commons, and here's the link to that. Switching gears yet again, this is not related to the previous discussion on Pascal's triangle and Fibonacci numbers. This is more of a probability question. In a group of 20 people, what is the probability that at least 2 have the same birthday? How many people do we need to have at least 50% chance that 2 people have the same birthday? So this problem I've seen for years. It's in different puzzle books on the internet now, and it's the number. If you haven't looked at it, the numbers. The answer to the second question here is smaller than what you might think if you just kind of guessed off the top of your head. So I'll give you a moment to think about that, and you may want to pause here, and then I'll come back in the following slides to explain it. Let's do the solution to the first of the 2 problems here. What we're going to do is compute the probability that no 2 people have the same birthday out of the 20, and then we'll subtract that from 1 to get the probability that at least 2 people have the same birthday. So to do that, we first calculate let's just show you the number here, the number of ways to assign different birthdays to 20 people. So the first person, there will be 365 choices. Then if the second person did not have the same birthday as the first, there would be 364 possibilities for the second, and then 363 for the third, since he or she can't have the same birthday as either one of these 2, all the way down to 365 minus 19. So that's the total number of ways to assign or have, maybe assign is not the right word, you don't assign birthdays to people, but the total number of ways for 20 people to have different birthdays. This is the total number of possibilities. And then if you count the total number of possible birthdays for 20 people, each person has 365 possibilities, and so it's just 365 to the 20th. And again, I'm leaving out, or not again, but I'm leaving out leap year just as a note. So we have 365 days in the year for this problem. So to get the probability of no shared birthdays, it's just this product here divided by the total number of possible birthday combinations for 20 people. And that would be 0.588656 approximately. And so the probability we're interested in is at least 2 birthdays are shared between the people in this group of 20, and that's 1 minus having no shared birthday dates. So it's 1 minus this, and it's around 41%. So for most people, including myself, who are seeing this problem for the first time, it's the number is higher than you would think. And so the second question, we're already pretty close to it, right? We wanted to know what was the least number of people in our group to guarantee at least 50%. So it's a few more, and I'll show you that on the next slide. So we're going to use a trial and error solution here. We got pretty close to the answer already. We just first note that if we had n people in our group, the probability of no 2 people sharing the same birthday is basically 365 to the n power on the denominator, and then it's the pattern we had before, 365 times 364, all the way down to 365 minus n plus 1. If you recall, when we had 20 on the previous slide, so that was minus 19 from 365. And then using that formula and taking note that what we really want is 1 minus the, this probability here. We can try it for 22. We put 22. We already did it for 20, and it was getting close. So we go up a few more people, 22, and we get probability for about 47.6% chance of at least 2 people having the same birthday. And then when you put in n equals 23, you get over 50% for the first time. So kind of amazing, right? Only 23 people in the room, and randomly, no particular selection of those people, and there would be almost a 51% chance that at least 2 of them have the same birth date. We have one last puzzle in this lesson. I'm going to give you the answer in lesson number 7, and we'll just state it here. So the puzzle comes from Raymond Smullyan. If you haven't heard of him, he's a logician, someone who's an expert in logic. He's written, I don't know, maybe a dozen or a dozen and a half books. Many of them are puzzle books with logic puzzles in them. He's very creative. He was publishing books up until his mid to late 90s. He's passed away a few years ago. I think he was maybe 97 years old. And his books are available on Amazon. In fact, when I give you the answer in the next lesson, I'll give you some references to his book. But let's look at his puzzle here. So you're confronted with 2 doors and 2 guards. One of the guards always lies or gives you untruths, maybe it's a better way of saying it, and the other guard always gives you the truth. One door leads to heaven and one to hell, and the puzzle is to find out which door leads to heaven by asking one of the guards a question. So you get one question. It doesn't need to be a yes or no question, but you get one question to one guard, and just to be clear, you don't know what door is being guarded by which guard. So 2 doors, one to heaven, one to hell, and 2 guards, but we don't know which one they're guarding. And you get one question to hopefully find out, which door you should go through. So we'll discuss this and give you an answer at the beginning of lesson number 7.